Jonathan is the founder and the CEO of a company called MSE International. And I'm sure he will tell you something about that. He has a good pedigree. So he has a good pedigree with qualifications from, first of all, Cambridge University and Cranfield Institute of Technology, or probably Cranfield University, and also from Imperial College in London. So he knows a lot about the seas and the oceans because that's part of his responsibility in MSE International. And his theme tonight, so maybe you can move on to your title slide. From sail to coal to oil, where next for shipping? This should be of interest to all of us. Little fact, 95% of the volume of goods that come into the UK and go out of the UK travel by sea. And 55% by value, so that takes into account all the insurance business and things like that. So without sea travel, we are stuck. And so what is the future of shipping into the future? So, Jonathan, the floor is yours.
Well, thank you. Thank you very much. This sounds a bit loud. Can we just reduce the gain a bit? Let's try that. That's better. Yep, perfect. Well, thank you very much for having me to speak. It's a great honour, and it's always a great pleasure, actually, to talk about something which is so dear to my heart. I've got a few slides to go through and hopefully to entertain you. But if I get carried away and go on, then just tell me to shut up and we can get on to the questions. But what I'd like to do, well, first of all, a little bit about MSE International. We're a very unusual company. We bring other companies and universities together to solve problems affecting the marine and maritime industries. I've been working in those industries all my career, loved it, or still love it. And but we've, like every industry, we're facing challenges, environmental, economic, and so on. So we need new solutions, and that's what we try to do, play a little role to bring people together to build prototypes and hopefully overcome those sorts of problems. So what I'm going to do this evening, I'm going to first of all look backwards to history, because of course we've had a maritime industry for half a millennium at least, and in that time we've been through various transitions. So it's nothing really new, and we can learn a lot from looking at how things have worked out in the past. I'm then going to take a little bit of a stock take on the transition that we're going through now, as we try to change the fuels that we use. And then I'm going to just look at some of the technologies and interesting things. I'm guessing there's quite a few sort of technical people in the audience who'll be interested in some of the details. So I'm just going to describe some of the things that we're now doing, and some of the really, in some cases, very surprising results that are coming out. So, a bit of history. The vessel on the top right is actually the one that my great-great-uncle used to be skipper of, back end of the 19th century, sailing out of Swansea docks. And what a beautiful vessel it is. Obviously sail. It operated on the India route and was the fastest thing on the water. Built somewhat surprisingly in 1871, given that the SS Great Britain, a steamship, was launched in 1844, a quarter of a century earlier. So lesson number one is that these transitions don't happen quickly. They take decades to happen. And we should always bear that in mind when we look at what's happening today. The other rather curious thing, which you may have noticed, is that the SS Great Britain, despite being a steamship, has masts. And the reason it has masts is because it was designed by Brunel, wanted to hedge their bets. So they wanted to be able to use sail when it was convenient, and perhaps more importantly, when it was profitable to use sail. So the SS Great Britain was actually a dual fuel ship. It could run on steam when it needed to, when the journey needed it, but equally, if it would save money, they could use sail as well. So again, interesting lesson for what we might be going through in the present time. So then we go on to the next transition, which was coal to oil. And in some respects, this was a much easier one. Because what actually happened is that the old steam boilers that were in the SS Great Britain were simply replaced by oil boilers. They were still very inefficient external combustion engines. And that was their undoing, really. I mean, the Kensington, it wasn't used, it didn't have a very long life because it was just too expensive. And what really made the difference was, of course, the internal combustion engine. And this is the Selandia, which was an incredibly interesting vessel in the sense that it was so far ahead of its time. And that had internal combustion engine, much more efficient, no funnel, of course. They integrated the exhaust into the rear mast. And that is quite close to where we still are, with the exception that diesel was replaced by heavy fuel oil because of cost. Maritime is very good at using the rubbish that no one else wants, and so that was what drove that change. And a lot of heavy fuel oil is still being used today, but that is really what the current transition is about. So that's the end of the history lesson, but some really important lessons to be learned from that experience. I'm not going to spend any time on this, it's really boring, but just to make the point that these days it's not just about economics, it's also about the law. And regulation is now pushing very hard on shipping companies to reduce their emissions, and there are various regulations which are requiring certain reductions in carbon emissions to be achieved by certain dates. So this is really, pushing things along quite rapidly. In light of which, you will probably be quite surprised by the next slide, because this is now the. I'm going to take you through this. Don't worry, you can't read all the detail. But what this is on the right, you've got the order book. That is to say, the ships which are being ordered today, not yet existing, they're being ordered, so they're going to be built and then launched maybe in 3 years' time, by the number of ships and by the tonnage of those ships. And what is extraordinary is if you look at the number of ships, nearly 3/4 are using conventional fuels. So you might be thinking, are these people mad? All this regulation coming along, and yet they're still going on with the old fuel, and these ships are going to last 25 years, so they'll still be in service, most of them, by 2050, when we're meant to be net zero. So what's going on? And the answer is that companies are hedging their bets. And there are some plan Bs, if you like, which are available to companies. It's a bit of a gamble, but biodiesel is one option. So they have their ship, and when they can't burn fossil fuels anymore, they move across to a drop-in replacement, which is biodiesel. So fair enough, that might work. I think it's a little bit unlikely, because I've got a little bit of data down there. There simply isn't enough of it by a massive margin. And so some people are going to be disappointed. They're simply not going to be able to buy this stuff. But the other one, which I'm going to come back to in a moment, is carbon capture and storage, which would go onto the ship to absorb the carbon before it's emitted to the atmosphere. And I'll come back to that in a minute. But what does this mean actually for when you look at the world fleet in the future decades? What does it look like in terms of the kind of fuels they're going to be burning? And fortunately, the heavy lifting analysis has been done by a company called DNV, and they've produced this. And again, I'll take you through this because it's a bit of a mouthful. But let me just point out that on this graph here, this is the graph showing the numbers of the ships, which are the total height of each bar, and then the different colours represent what energy source they're using. So these greys, the light grey, the mid grey and the dark grey here, are ships using unabated fossil fuels. And as you will see, unsurprisingly, it drops and drops and drops until it gets to almost zero by 2050, as you would expect, because the regulation requires it. But the grey on the top, this bit here, is actually the ships which DNV reckons will have to install carbon capture, because they will be the ones that I've mentioned in the previous slide. They're on order now. They're going to have those ships. They're going to want to use them. So they're going to use them by putting in carbon capture and storage. And we'll look at what that entails in a moment. This green bit is the biofuel bit. And as you can see, it's quite limited, and it doesn't last long because better solutions appear. As biofuels get really expensive, as they will, you're looking at a better solution. And the bit in the middle here are the new fuels, so-called e-fuels, made from renewable energy, or using renewable energy, so inherently zero carbon, but currently extremely expensive and probably always quite expensive. So this is the trade-offs that companies are making now, how to juggle their response to this changing landscape. And I think that the ability to use their existing vessels by hook or by crook, retrofitting whatever they need to retrofit, is a key part of what they're planning to do. Now the biofuel bit needs a little bit more scrutiny, and this is because you never quite know where it's coming from. So if you're buying biofuel from, let's say, Indonesia, how do you know that has been properly generated, as opposed to someone chopping down a tropical rainforest and planting palm oil to make some biofuel and a quick buck? You need to know that, because chopping down a tropical rainforest and planting palm oil is massively damaging. It's massively negative from a carbon perspective. So this really would be a massive disaster if this happened at scale. So we have this chain of custody which essentially tries to keep track on where the biofuel is coming from, how it's moved around, how it's distributed, and where it's used. So that's a long way of saying we've got to really police this very carefully. And I'm very skeptical, because we know from the fishing sector how easy it is to falsify the paperwork. And I think this could turn into an unmitigated disaster if we're not very careful. So treat with caution, I think, would be my message on that. Now, coming on to the other option, which is the onboard carbon capture and storage. I'll just a little bit of word about what this is. So on the ship here, what you've got is the conventional engine, and it discharges its flue up through the funnel here, or through the funnel here. And what you do is you divert the flue gas before it is discharged, and you absorb the carbon in a chemical carrier, which will absorb carbon, and then you process the chemical carrier to release the carbon, and then you liquefy it to go into this storage tank on the vessel. When the vessel gets into port, you take the carbon dioxide from the tank, you offload it, you do something clever with it in the port to store it. You then have to distribute the carbon dioxide, and people are looking at re-injecting it and so on. The problem with it, and it's a big problem, is that it's an incredibly inefficient process. If you just look at the amount of fuel you have to burn to drive the carbon capture, it's about 40% of what the vessel is burning anyway. So this is a massive cost overhead. Then you've got to factor in the fact that the process only absorbs about 80% of the carbon anyway. And suddenly you realise, actually, we're spending all this money and we're gaining a very small advantage. So I think we're fairly sceptical about this particular process. So, but there is a better solution. And this is the better solution. It's one that we're working up a collaboration with the University of Strathclyde at the moment, who've built an early prototype, not on a ship, but just to prove the process. And what it does is it again takes the exhaust gas here, but it converts it into a fertilizer. So you're not trying to convert it to carbon dioxide and extract it. You're using the carbon dioxide to create another product. And of course, fertilizer is needed. There's a need for fertilizer, particularly with wars in Middle East and so on and so forth. So you're actually creating a product which has got real value, and so this, we think, is probably the way that carbon capture will go. Not necessarily this particular process. There's another UK company called Seabound, which is doing a reasonably similar technology. So there are lots of these ideas, typically small companies coming up with bright ideas, and we need to now to commercialize those and get them up to scale. But this seems to us to be an important technology because we have to have this carbon capture. Otherwise, loads of the world, half of the world fleet is going to be idle because they can't operate them. So there we are with the carbon capture. The other big area which is interesting is the hybrid ship. These are ships which will have a small conventional engine, but most of the energy that's used by the ship when it's traveling between A and B is electric. And you simply use the small engine to effectively extend the range of the ship, because it can't do the whole journey on electric alone. The batteries are not big enough. And so this is just an example. I'm not going to go into great detail, but you can see that you've got a load of propellers at the bottom here, fine, electric motors driving them. You've got some big batteries which do most of the heavy lifting in terms of the energy supply. You recharge the batteries in port, and then you use the energy as you're underway. But some diesel engines which will do the topping up if you haven't got enough energy in the batteries. And this can save an enormous amount of carbon, depending a little bit on the route that the ship is operating on. But these technologies are advancing very rapidly, with some of the technologies around new materials, making these motors much more efficient, everything that can all help to make the ship more efficient and use therefore less fuel. Quite an interesting statistic at the bottom here. Some of the new electric motors that we're talking to some companies about using now, they have what's called a power to weight ratio of 20 kilowatts per kilogram, with an ambition to go up towards 50 kilowatts per kilogram. But if you look at a conventional ship's engine burning heavy fuel oil, that has a power to weight ratio of approximately 0.2 kilowatts per kilogram. That's 100 times worse. That gives you a flavor for how technology is really helping us here. So just a little bit more example on that. So this is an example of the way that the technology is now being used. This is what's called a podded drive. I'll talk about the azimuth in a minute, but the important thing is that the pod is this bit here, effectively. And this pod contains an electric motor, and the company that we're talking to, Helix, they've developed their technology with the performance, the motorsport sector, which of course, if you're developing a car for motorsport, you've got to have a really good power to weight ratio. It's what makes the car a winner or not. And so they're expert in this. And what they're starting to do now is to marinize that technology so it can go into this sort of drive. So you've got the electric motor, normally a gearbox, and a propeller on the end. And the big sort of game changer with this particular technology is this compact size. When you've got a ship or indeed any other object passing through the water, drag is a big factor. It's the drag which governs how much power the vessel needs to propel it, which in turn governs how much fuel you need to burn. And these podded drives with very efficient motors in them have a very small cross-sectional area. So the drag on this podded drive will be a lot lower than on a conventional one. And it means that you can start to use these sorts of drives on a much wider range of vessels, even ones that need to go fast. So we're very excited about this. I think these are the sorts of new technologies which are going to supercharge the transition of our maritime industries. The azimuth, incidentally, just refers to the fact that this pod can be hung down from the hull, so it's sticking down below the vessel. But you can rotate it because it's got nothing connecting it to the hull apart from the little stalk. There's normally a mounting stalk about here which will connect it to the hull of the ship. But you can rotate it around that, so you don't need a rudder. You can just steer the vessel by turning this podded drive. And it means you can actually turn a ship on a sixpence, because you can have one going if you've got two of these on the ship, one can be pulling one way, the other can be pushing the other way, and the ship will just rotate. You can't do that with a conventional ship. So a lot of operational advantages with this kind of technology as well. Okay, so this is all very well. These are all interesting technologies. What does it actually mean in terms of real ships? So this is a project we did 6 years ago now. It's extraordinary how time flies. But some of you may recognize this one. This is the Gosport Ferry. And the company that we work with, one of the companies we work with, but the naval architects that we work with and have been for many, many years, is a company called Holder. Again, some of you may have come across it. They have a base in Portsmouth and also in London. They designed this vessel originally. This is a conventionally fueled vessel at the moment. It runs on diesel fuel. And what we did with them, or we asked them to redesign the vessel as if the client had said, make this electric. What would the vessel come out like? Would it work? So that's what we did. And by the time we'd done the optimization, what they ended up with was some batteries on this vessel, which would give it a 1 hour endurance, a lot more. I mean, it takes about 12 minutes, I think, to do the crossing from Gosport to Portsmouth. So you've got a lot of leeway in there. And interestingly, for this particular exercise, we were using something called a flow battery. And a flow battery is different from the average battery that you will all be familiar with, in the sense that it has a liquid which you can pump around the battery, and that takes the place of the solid material inside a conventional battery. But it does mean that you can actually recharge these devices hydraulically. You pump in fresh electrolyte and take out the spent electrolyte, so you don't have to bother with electric transfer, which we thought might be an advantage. We were wrong, as it happens, but anyway. You win some and you lose some in this game. But the really interesting result was that the time we'd done all this, we ended up with a vessel that was lighter than the one that was actually built. And this was completely counterintuitive. Everyone thought it would be much heavier because of the batteries, they will weigh an enormous amount and so on. But actually it was lighter. And one of the reasons is that it was a much simpler vessel. If you think about it, when you're burning fuel, the weight of the vessel is decreasing all the time because you're using fuel. That weight is going up the funnel, and therefore to keep the vessel at the same level so people can drive their cars onto it when it's at berth, you have to ballast it. So you take on water to replace the fuel that's been burnt. And that all takes space, it all takes weight. When you've got a battery, you don't need that because the weight isn't changing. So we've got a much simpler vessel, and as it turns out, a lighter vessel. So this was really encouraging and really spurred us on to do a lot more. But the key, I suppose, the driver which is making us absolutely convinced that electric has got an enormously important role to play in this industry, is what's happening with battery prices. And this is a graph showing you this is for lithium-ion batteries, the sort that are in electric cars today. And the red line is what the price of these batteries has done over time. This is 2010 on the left here, when lithium-ion batteries were costing about $1,200 per kilowatt hour, right the way down to 2023 when the analysis was done, when they were a little bit more than 100. So they've come down by more than a factor of 10 in that time. But the other really interesting thing about this figure is that the dotted lines were what experts thought battery prices were going to do in the future. And every single one of them underestimated the extent to which prices would drop. And the reason for that is that they didn't consider one of the most important drivers of price reduction, which is that as things get cheaper, more and more people can use them. So haulage companies suddenly realize, batteries are cheap enough now, we can use them on trucks. Mining companies said, we can use batteries on this, that and the other. So suddenly the market mushrooms. And with that you get a load of investment coming in, which means that the rate at which the price can come down accelerates. And so that has really transformed the situation. The EV, the electric vehicle sector, of course, has been largely responsible. But all these other sectors piling in to use batteries has massively increased the rate at which prices can come down. And when we start looking at what might come after lithium-ion, and we're starting working on a technology called sodium ion, which is a battery technology which has got some real advantages over lithium, particularly for ships actually, because it's got a lower risk of what they call thermal runaway. This is something you've read about in the papers, where someone's car suddenly bursts into flame. Well, that's thermal runaway. And sodium ion is much less susceptible to that kind of problem, which on a ship is actually pretty important. You don't want to be on a ship when the cargo goes boom. So sodium ion is of interest, but the other thing is it could be really cheap because it doesn't need lithium. Lithium is becoming a really expensive commodity now, and they're all made in China. And we're getting regular bulletins from Chinese suppliers saying, sorry, we're going to have to put prices up now because the lithium's got so expensive. Well, the sodium-ion batteries, they don't need any materials from, shall we say, geopolitically challenged parts of the world. And so these can all be made here in the UK. And we've got an emerging supply chain in the UK to build these batteries. So with a fair wind, this could be something that really works well for us. And we're talking about here, the projections are something like $10 per kilowatt hour for a for a sodium ion battery. Again, a factor of 10 lower than lithium at the moment. So, once we start getting to that level, anything is possible. So, very interesting times. You might be wondering why I haven't said very much about making the ships more efficient. Been concentrating only on what energy type it's burning. Well, there is of course a lot of progress that could be made and is being made in terms of improving efficiency. I'm just going to touch on that because it does make the problem of the energy transition much easier if you're using less of the stuff. So this is, and you'll see here this interesting device here. This is what's called a Flettner rotor. And it's basically a sail. It doesn't look like it, but it is actually a sail. And what you do is you rotate, you have a motor which rotates this cylinder, which is mounted vertically on the deck. And that, in a crosswind, means that the vessel gets a propulsion force moving forward. So you can put these in and you can reduce your fuel use by probably something in the region of 15% with these devices. So wind assist is really important. Remember my first slide with the SS Great Britain with its wind assist? Nothing new in the world. But of course, as soon as you've got sails, you've got to think about your course because you need to find where the best wind is. So this bottom diagram is work that's going on, and there's some young companies starting up now doing very clever software which will determine what the best route of the vessel is. So you avoid going through, for example, very rough water which uses more energy. So you can avoid those sorts of storms, you can avoid cyclones, you can basically, and the software optimizes the route to minimize the amount of fuel that needs to be burnt. When you combine wind assist with route optimization, we reckon you can get something like a 25% fuel saving. That's a very significant saving. So, and this can be done at pretty low cost actually. So there's a lot that can be achieved here. And one of the enablers of all this clever IT on ships, which is accelerating apace as we speak, is the availability of satellite communication. Now this is another rather interesting graph. This is the number of satellites in Earth orbit starting in 1960, 1980, 2000, 2020. So you can see for decades it was just gradually increasing. And then, of course, Elon Musk comes along and woof, up we go. And that's Starlink low Earth orbit satellites. Then you've got, of course, not wishing to be outdone, Bezos coming in with his Blue Origin. And the reckoning is that we'll have about 60,000 active satellites in orbit by 2030. So that's way above the ceiling on this graph. What's that actually doing for us? What it's meaning is that we can suddenly use these satellites for communicating from a ship wherever it is on the ocean. Historically, that was completely impossible. The early Inmarsat communications were really expensive. Now you can do it for pennies. And so it means that you can put a lot of instrumentation on ships to optimize how it is performing, how it is being operated, and reduce its fuel use. And that's due to this explosion in worldwide communications capability. So, what else is that doing? Well, it's meaning that we can suddenly start to think about autonomous ships. I'm sure you've probably read about the autonomous cars having shall we say, a mixed gestation as they iron out the problems. But I'm sure they will iron them out, and I'm sure we will all be moving around in autonomously or driverless cars at some point. But the same is starting to happen on our seas and oceans. And this is a project that we led a few years ago, which was essentially designed this vessel here. Some of you might be familiar with a vessel that carries wind turbine blades from the Isle of Wight to Portsmouth, and well, actually they go to Fawley first for finishing, and then they go to Portsmouth. And that's a vessel called the Blade Runner, and it's a conventional diesel-fueled vessel. This one here is one we designed. Again, our friends at Holder did this work, and the brief was design a vessel which can not only be electric but can also be autonomous. So you don't have to have a crew on this vessel. It sets off from Isle of Wight with its turbine blade, and it sails on a predetermined route. It takes avoiding action if it's going to hit anything, of course. But it means you can, this is important because autonomy and efficiency go hand in hand. If you don't need all the life support systems that you need on a crewed vessel, you can make it much simpler, you can make it much lighter. And so this vessel was demonstrating that it's possible to do that. We haven't built this yet. Unfortunately, Vestas changed their strategy just when we were halfway through doing this, which is extremely inconvenient of them. But sadly, these things happen. But we have taken this forward, and we've developed a protocol for ports to use so they can support autonomous vessels. And this is just some work to look at risk assessment in the very crowded Solent. I mean, if you can do something autonomous in the Solent, you can do it anywhere because it's the most crowded waterway in the world. So a good testing ground for us. So all interesting stuff. The sort of vessels which we think could use this, sort of the ferry type, the ferry market, with using not necessarily with full autonomy, but with some automation, so it can be integrated with how much energy it's going to need when it gets to port, which the port obviously needs to know. So that could be very handy. Survey vessels, as some of you may know, we're having to do more and more surveying. Every time you build an offshore wind farm, you have to do a load of surveys to prove that your wind farm isn't causing environmental damage. And so you do a survey before you build the thing, and then you have to do regular surveys every year while it's operational, so you can confirm that no untoward impact has been caused. That's very expensive using conventional survey vessels. So the next generation will be autonomous, which will go backwards, a bit like mowing the lawn. You go backwards and forwards over your area of interest, collecting all the data you need, and that will reduce costs enormously. So there are some particular vessel types which we think are suitable for this and will be the pioneers. And we want the Solent to be in the leading edge on that. So we're working on a number of projects to demonstrate these sorts of vessels. But the final thing I wanted to touch on now really is what happens in port. And this is just the last few slides before I close. Clearly, if you've got an electric vessel, it's got a load of batteries on board, you've got to recharge them. And that happens in port, obviously. And so ships will connect up to electricity supplies in the port. And equally, even non-electric ships will have to connect up because they've still got, let's say, a cross-channel ferry. It's got loads of air conditioning to keep the passengers happy. And that has to be powered somehow. And ships are not going to be able to power those by operating their onboard engines in future. So they have to get the energy electrically from the shore. And this is called shore power. Now this diagram is quite instructive. What it's doing is comparing different ways of getting that electricity onto the ship. Now, if you connect it directly to the grid, which is on the right here, the losses are extremely low. the transformers might have a few percent loss and so on. So the analysis says that you would have to provide 1.09, so about 10%, just under 10% of the electricity the ship needs, you lose in losses. But if you generate the electricity using a fuel, so you convert the electricity into a fuel which you then burn on the ship as a zero emissions fuel, it's catastrophic. Because unless you're in Norway is unique in the world, but for everyone else, particularly if you look at somewhere like China, where they've got still quite a lot of coal-fired generation, it means that the electricity in your grid is very high carbon content. And so you're much worse off if you use grid electricity, which is coming from a very high carbon grid, than if you're not. So Norway, they've got all this hydropower, and their grid is pretty well zero carbon, but they are unique, as I said, very fortunate and unique. So we have to be very careful how we go about this. We don't want to make things worse. And so the conclusion is that it's far better to make the whole thing electric, because you don't have any of these big losses. And this on the left here, you've got what is how much energy you lose if you take your electricity, you convert it into one of those e-fuels I mentioned earlier, which is very inefficient. Then you burn the e-fuels in a generator to generate the electricity, and that's also very inefficient. So you need over 4 times as much energy on the input as you actually get coming out for the ship to use. Clearly not a good thing to do. Making this pay, because of course the ship operator, they don't want to be paying high electricity prices, and so the question is, well, what does the port do about that? How do they sell electricity to a ship profitably? And it's extremely difficult, because as we all know from our electricity bills, we have to pay a lot per kilowatt hour of energy that we use, and the same is true for ports. A lot more than the ship would have to pay if it was using its own generators. So there's a massive incentive for the ship operator to surreptitiously use means of getting power without having to pay the high price of grid electricity in the UK at the moment. But batteries come to our rescue again. And the reason is, this is just a little schematic of some work we're doing with on the Isle of Wight with Cowes Harbour Commission, and other ports actually as well. But the idea is that you have your grid connection, you have your various converters to turn it from AC into DC, direct current, and you have a battery. And what the battery does is it means that you don't have to pay, if you're on some of you may be on octopus tariffs for your electricity. If you use electricity at a cheap time of day, you could pay a very small price for it. And what the battery does is it means that the port can take advantage of that same mechanism. So they can buy their electricity when it's maybe 5 pence a kilowatt hour. They can store it, and then when the vessel comes alongside and needs power, which might be at 5 in the afternoon when electricity prices are very high, you can simply provide the electricity from the battery. This can transform the economics of this process. So batteries, really, we have to have big batteries in our ports, and that's something we're working on a great deal at the moment. It's also quite interesting because ports can do more than that. The grid, with all the offshore wind that's being fed into the grid, is becoming unstable. And because electricity is being generated at times when the wind's blowing, which isn't necessarily the time when you really need it, it means that sometimes we're generating more than we can use, sometimes we haven't got enough. So this is why the grid operator needs to have access to what effectively is emergency electricity. Now the ports can be a provider of emergency electricity. When they don't need to supply power to a ship, they can sell their battery capacity to the grid operator and say, if you need extra, we've got some. And that can generate you a lot of money. So these are the ways in which ports are now, as they electrify, are becoming really completely different businesses. They're not just taking in ships and unloading cargo, they're becoming energy hubs in their own right. And this is just illustrated in this is now some work we're doing with Portsmouth. Portsmouth, they've got some now facilities for connecting electricity at very high power, we're talking about 10 megawatts here, to ships that come in. They've got a grid connection. At the moment, they don't have batteries. Big mistake. We persuaded them to put in a very small one as proof of concept, which was actually one we installed for them about 5 years ago. So they recycled it and put it into this system. But purely just to show how it would work. It's nowhere near big enough. And now we're working with them on a project to try and get the investment for them to put some really big batteries in there. So it's retrofitting. They've got some big solar panels. They've got about a megawatt peak of solar capacity in the port. But again, they didn't know what they were doing really, so that's being separately contracted. And they can't use it in the port because it's already been sold to someone else. So there's a lot that we're learning as we go here. It's always the way. And the really interesting bit is what happens over here when we get clever and we can start selling these services back to the grid. That's when we can really make these systems work economically. And we're on the case. That will happen. So, conclusion. One of the important lessons from both history and indeed today is that infrastructure, and particularly energy distribution infrastructure, is absolutely crucial. And if you think back to when ships moved to coal, the only reason that they could do that was because the railways had already got the infrastructure to distribute coal all around the country. And of course railways in those days burnt coal, so they were absolutely instrumental in the shipping sector suddenly waking up and saying, oh, we got all this coal, we could use that. So they piggybacked on the railways effectively to make that transition to coal. And the same is going to happen this time round. It's all going to depend on infrastructure. We don't have a hydrogen infrastructure at the moment, which is one of the reasons why hydrogen hasn't really happened to the extent that people thought it was going to. It's infrastructure which was holding it back and still is holding it back today. And probably that ship has sailed, if you'll pardon the pun, because electricity and battery storage is now becoming so dominant that I think hydrogen has probably missed the boat. I think the other factor which is becoming clear is that, and I've already sort of said it in the last few moments really, is that we're becoming much more interdependent with other sectors. Certainly in terms of getting that scale, all that battery price reduction, that's becoming possible because other sectors are also needing those batteries. But we're also competing for resources. So when I talk about biofuels, the problem there, and the reason why I don't think there's a massive future for biofuels in the shipping industry, is because everyone else wants them, including some sectors which can pay more than shipping. So, understanding those interdependencies is important to really map the future. And finally, I think there is a load of what we will call key enabling technologies, which are really giving impetus to this transition. One being digital, so AI, better understanding and modeling of how ships perform, how we can make them perform better, and of course energy, batteries, carbon capture and storage has got a vital role to play, and in making our ships ever more efficient. So there we go, that's the view as we see it for where next for shipping. Happy to answer any questions.